Good morning, everyone. Welcome back. Uh, during the last lecture, we talked about metamerism and how metameric failure occurs. We talked about a specific type of metameric failure, which can be seen in this particular slide in front of you, which is known as illuminant metameric failure. That means these two objects having actually different colors appear to be of the same color under one illuminant condition. For example, let this be D65 and it appears to be having different colors under a different illumination condition. This is known as illuminant metameric failure. Now I think I have already described the reason why why metamerism happens, and ultimately under what circumstances metameric failure happens. So this is a little bit of paradoxical nature, because as soon as something, if you could understand the idea or the working principle behind metamerism, I think it will be clearer to you that as soon as metamerism occurs, there is a fair to good amount of chance that metameric failures will also occur. Right? So in this, before moving on to the next topic, which is color difference, I have a question for you. That take a look at this particular slide. What is happening? We have got two specimens, specimen B and specimen A. Now they are having two different types of SPDs, right? Their SPDs are fairly different from each other, yet under one illumination condition they are appearing to be of the same color. But as soon as we are changing the illuminant, that is, we are using illuminant A, specimen B is appearing to be of red color, while specimen B is appearing to be of blue color. Now my question to you is, why is it that specimen, what is that factor, or what might be the the guiding reasons behind specimen B to have this reddish appearance? In order to understand, or in order to answer the question, I will give you two hints. The first hint is, check out the SPD for these two specimens, specimen A and specimen B, and specifically just focus your attention in the red wavelength region of the SPD of the two specimens. Notice, just pause the video here for a minute, or just try to take a screenshot on your phone or your computer, whatever you are using. This is your hint number 1. This is your hint number 1 in order to answer this particular question. Okay. Your hint number 2 is the SPD of the illuminant that you are using, that is illuminant A. So where did we see the SPD of illuminant A? In a previous slide. It was, I showed you in the previous slide, just when we were beginning to understand what colorimetry is. In one of those slides, I think we saw the SPD for the illuminant, various types of illuminants that we have. So let me just go on to that slide once again. So yes, here it is. Take a look at the dark blue line over here. This represents the SPD of illuminant A. See, this represents the SPD of illuminant A. Now notice this, the nature of this particular SPD, and also notice the yellow line, which represents the SPD of illuminant D65. Just pause the video here for a minute, take a look at it, or take a screenshot. This is your hint number 2. Now using this both hints, that is hint number 1 and hint number 2, try to figure out why is that under illuminant A, that particular this particular specimen B is having a reddish type of color appearance. Just try to figure this out on your own. I will and let me know via email, so I will be able to answer the question, answer this particular question in the next lecture that we have. Okay. So okay, so this is okay. Now we move on from metamerism. We have completed metamerism in this lecture. Now we will come to the point which is known as color difference. So I think while talking about the XY color space, I have, yeah, the XY color space or chromaticity diagram. I already gave you some idea about distance between the two colors. So for example, you take one color over here, which is A, and okay, another color over here, which is B. Now what is the chromaticity coordinate of this A and B? You can just, how to find it out? Just draw a line. I'm sorry, this should have been a straight line, but you know, vertically 1 and horizontally 1. So you want to find the ordinate and abscissa for this point A. So roughly what will be your approximation? 0.35 and 0.6, right? So the chromaticity coordinate for color A, which is actually green in color, some shade of green, it has a chromaticity coordinate of 0.3 and 0.5. So similarly, B is another color which is magentaish in nature. So it is having a x value of x coordinate of 0.51 and y value of 0.3. So 0.51 comma 0.3. Now if I ask you to find out the distance between these two colors, in coordinate geometry in your lower classes, you have already seen, in any coordinate space, how do you find out the distance between any two points? You find out what is known as the Euclidean distance. That means in this case, if this is x1, this is y1, this is x2, this is y2, then the distance AB will be equal to root over of x1 minus x2 whole square plus y1 minus y2 whole square, 51 whole square plus y1 is 0.6 minus 0.3 whole square. So you will get a value. So that distance, that value will be the distance between the two points A and B, right? So similarly you can find out, if I give you another point C and D, so similarly you can find out the distance between these two colors. So what are we essentially calculating? When we are calculating the distance between any two points in the XY chromaticity space or any color space for that matter, what are we exactly calculating? We are calculating the difference between two colors. See, in this case A is green and B is blue. C is one shade of maybe greenish blue or something. D is cyan in nature. So this distance between any two points in the color space is known as the color difference between two colors. So color difference is nothing but the mathematical method using which we can find out the distance between two colors in any color space, essentially giving us an idea about how, or the metric regarding how one color differs from the other, or by how much one color differs from the other. This distance between two colors in the coordinate space is noted as delta E. E stands for Empfindung. Okay, so this is actually maybe the spelling is a little bit you have to check it with Wikipedia or something, but Empfindung is basically means a difference between color perception. This is what Empfindung is. So essentially, when we are talking about distance between two colors A and B, or distance between two colors C and D, and we are getting some value, it means what? It means that how much two colors are different from each other. That is how much, by how much we perceive those colors to be different. Okay, so here we will see one this formula that I just told now. I'll show you in one of the slides. Yeah, there you have it. Yes, so in the previous case, we in this xy coordinate system, how did we define delta E? We defined delta E as root over x1 minus x2 whole square plus y1 minus y2 whole square. So now, as I told you, color difference or distance between colors is a metric that can be applied to any color space for that matter, right? So in this context, here we will be measuring the distance between two colors in the LAB color space, where one color 1 is having colorimetric value L1 A1 B1, and color 2 is having colorimetric value of L2 A2 B2. Now in order to find out the difference between these two colors, I need to find what? I need to find the distance between these two colors in the LAB color space. Therefore, how can it be found out? Root over L2 minus L1 whole square, since it is squared value. So L1 minus L2 whole square and L2 minus L1 whole square will give you the same result. L2 minus L1 whole square plus A2 minus A1 whole square plus etc. Now, so if I give you to calculate the, if I have tri-stimulus value, if I am using the XYZ color space, and I tell you one color is having coordinate space of this thing and the second color is having coordinate space of this. So in that context, how will you find out? By the same method, that is root over x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square, right? So that will be the delta E, the difference between two colors, the perceptible difference between two colors. Now there is one commonly referred value in standard literature which is known as the just noticeable difference. It has been noted in various studies, although I do not agree with it, and neither do a lot of the people who actually work in the field of color science agree with it. That however, let me just inform you on this. There is some terminology which is known as just noticeable difference. It has been said that if the difference, let us say the difference between two colors is 2.2, it is said that if the difference between two colors is up to 2.3, then the human eye will not be able to perceive the difference between these two colors, right? So if it is nearly 2.3, you will not be able to identify or distinguish between the two colors. If it is 2.4, you will be able to identify the color. But there are so many exceptions to this rule. I mean, this doesn't hold true for all cases. I have personal experience where I have found that delta E was 1.5, yet the it was visually it was very different from each other, and so a whole lot of issues happen. Now the CIE also tried to mitigate this problem. You see, why is this problem happening in the first place? This problem is happening in the first place because of a very simple fact, that the mathematical derivation or mathematical formulation that defines the difference between two colors is not similar to how our eyes are perceiving the difference between those same colors. That means mathematically color difference does not match with our perceived color difference. This is a simple statement. I am repeating myself here. The mathematically defined difference between two colors does not always match with the visually perceived difference between two colors. যেটা অঙ্ক থেকে করে দুটো কালারের মধ্যে ডিফারেন্সটা পাচ্ছি, সেটা আমরা চোখে অনেক সময় ধরতে পারি না। যেটা বললাম যে হয়তো কালার ডিফারেন্স 1, 1.5, 2 এসছে, অথচ অনেকটা চোখে দেখে মনে হচ্ছে অনেকটা আলাদা কালারগুলো। তা তো হওয়া উচিত না, তাই না? যেটা ম্যাথমেটিক্যাল, যেটা আমাদের চোখ, মানে তখনই একটা ফুল প্রুফ সিস্টেম আমরা ডিজাইন করতে পারবো যখন আমাদের চোখে দেখে যতটা কালার ডিফারেন্স মনে হবে, ম্যাথমেটিক্যালিও ওরকম কাছাকাছি একটা আমাদের আইডিয়া। যদি কোনো দুটো কালারের মধ্যে ম্যাথমেটিক্যালি আমি 4 পাই ডেল্টা ই ডিফারেন্স, তাহলে অটোমেটিক্যালি চোখে দেখেও আমি বুঝতে পারবো যে অনেকটা তফাৎ দুটোর মধ্যে। কিন্তু যদি ডেল্টা ই ডিফারেন্স 1 কি 0.5 পাই, তাহলে চোখে দেখেও আমরা বুঝতে পারবো যে কালারের দুটোর মধ্যে খুব একটা ডিফারেন্স নেই। তাই হচ্ছে ব্যাপার। নাও the CIE also tried to mitigate this problem by revising this particular formula. This formula, এটা কি? This is only Euclidean distance in Cartesian, I mean in color space between two colors, right? But this was refined and revised in a later stage. এইবার এখন একটা রিভিশন হয়েছে, CMC ডেল্টা ই CMC দিয়ে একটা রিভিশন হয়েছে। এখানে দেখো আগেরটায় we used LAB color space or XYZ color space or XY color space etc. এখানে LCH color space ইউজ করা হচ্ছে, ঠিক? তো এখানে L2 minus L1 টা ফিক্স থাকলো, C2 minus C1 আর ডেল্টা H মানে H1 minus H2, এইগুলো সবই সেম থাকছে। কিন্তু এর সাথে সাথে অন্যান্য কিছু কনস্ট্যান্ট, অন্যান্য কিছু ওয়েইং ফ্যাক্টর এখানে অ্যাড করা হচ্ছে। এই যে SL, এসসি, এসএইচ এই ধরনের কিছু ওয়েটিং ফ্যাক্টর এখানে কিছু অ্যাড করা হচ্ছে টু দিস ইকুয়েশন। পরবর্তীকালে আবার রিভিশন হয় এই ফর্মুলাটা, সেটা 1994 এটা রিভাইজড হয়। So similarly you will be able to see that these are some additional terms that were added later on in 2000. It was further modified like this, so a whole lot of other terms were incorporated in the delta E formulation. এটার পারপাসটা কি? সিম্পল পারপাস, সেটা হচ্ছে আমার যে প্রবলেমটা নিয়ে আমি শুরু করলাম কথাটা, যে ম্যাথামেটিক্যালি দুটো কালারের মধ্যে যা ডিফারেন্স পাচ্ছি সেটা কিন্তু আমার চোখে অতটা ডিফারেন্স আমি ধরতে পারছি না, বা ম্যাথামেটিক্যালি খুব কম ডিফারেন্স থাকলে আমি চোখে অনেকটা ডিফারেন্স পাচ্ছি, তার মানে আমার ফর্মুলাটা ঠিক নয়। In that scenario, when the mathematically derived color difference between two colors does not match the visually perceived difference between the two colors, then only the problem arises. In order to mitigate this problem, the formula for delta E calculation was revised time and again by CIE. Now the principle is যে যেটা আমি চোখে দেখতে পাবো, যতটা কালার ডিফারেন্স আমি দুটো কালারের মধ্যে চোখে বুঝতে পারবো, ততটাই আমার ফর্মুলা থেকেও জানি, যা ম্যাথামেটিক্যালি জানো আমি অতটাই ডিফারেন্স তুলে ধরতে পারি। মানে যদি এই কোনো দুটো কালারের মধ্যে কালার ডিফারেন্স যদি এই ফর্মুলাটা থেকে আমি পাই 1, তাহলে আমার চোখে দেখে মনে হবে যে খুব একটা কালারের ডিফারেন্স নেই। বাট আলটিমেটলি ইউ সি, মাই পয়েন্ট ইজ নান অফ দিস ফর্মুলা ওয়ার্কস very precisely. কোন জায়গাটায় কাজ করি? in the industry when you go, most of the places they use this simple AB formula. This is known as the Euclidean formula. This is used across industries as a standard value, as a standard method to calculate the color difference. For most of the printing operations, graphic art operations, whenever we talk about calculating the color difference between any two colors, standard and batch, then we use this particular Euclidean difference between the two colors, this formula for calculating the color difference. But this is not the, here we do not face any problem. Sometimes we do, so we need to reformulate our ink, reformulate the spot colors used in the ink, so a whole lot of that is that requires to be happen, but that is a different issue. But the primary problem while revising these formulas were due to the appearance changes because of a variety of viewing conditions or illuminants that were basically used while visualizing certain colors. এইটা খুব বেশি করে ইউজ হয় when we watch or when we view colors in digital displays, like right now you are watching this video on a computer or your mobile phone. So when we visualize color, in those situations the viewing conditions vary widely because the backlit of varies from company to company, the way colors are reproduced by the LED sensors or arrays from one display to another display, one manufacturer to another manufacturer varies, even within the manufacturer from make to make it varies. So all this viewing, when the viewing condition changes, as I already told you previously, এই যে ড্রেসটা যেটা এক্সাম্পলটা দিলাম, যে একই ড্রেস বা মেটামারিক ফেলিয়ার যেগুলো হচ্ছে, এই যে ড্রেসের যে এক্সাম্পলটা দিলাম, যে একই ড্রেস is appearing to have different colors under different illumination condition. So এখানে আমি কি করে কালার ডিফারেন্সটা বের করব? By using what formula? Under one illumination condition color difference will be 1, and whenever we are changing the illumination condition the color difference changes. So in order to take into account all these factors, varying illumination condition, chromatic adaptation, simultaneous contrast, all of these factors, hue shift, all these things, we have something which is known as the color appearance modeling. The father of color appearance modeling is Johann von Kreis. I think I have a picture of him somewhere. Let me just I think I had one of he is known as the father of appearance modeling. Appearance modeling is not the scope of this class. It is for your higher classes when you go into further studies, but I'll just give you a brief idea that you have seen, and I have also talked about, that as soon as the illumination condition changes, the color appearance seems to change. So similarly in displays or for printed patches under different lighting conditions, the appearance seems to change. So only finding out the color difference, Euclidean distance or some other parameters, incorporating some other parameters, that is not sufficient a tool to calculate or identify the difference between actual difference between two colors. You need to consider other chromatic factors also. Especially you need to consider the illumination under which you are observing these two particular colors, be it printed patches, be it on the screen, etc. Also, you need to consider what is known as the chromatic adaptation models. In order to that has to be incorporated while calculating the difference between these two colors whenever you are viewing them. Only when you consider all this, I am not going to details of all those factors. You need to consider chromatic adaptation, hue shift, simultaneous contrast, the nature of illuminant that you are using. All these things you need to incorporate before calculating the difference between two colors. So only calculating color difference, that is Euclidean difference, or incorporating some additional parameters into those formula will not serve your purpose. That means it might serve your purpose if your intention is just to match your batch print with the standard print. That will serve your purpose. But ultimately, if you want precise color control over a whole lot of different platforms, a whole lot of different devices of different makes, different manufacturers, etc., you need to consider what is known as color appearance modeling. You need to consider all of this. So I'll just end this lecture with a famous quotation from Johann von Kreis, where he said that if someday, just take a look at this particular quotation here, if someday it becomes possible to recognize and to distinguish in an objective way the various effects of light by direct observation of the retina, people will perhaps recall with pitying smiles the efforts of previous decades which undertook to seek an understanding of the same phenomenon by such lengthy detours. But it is very heartening to observe or to note at this stage that when von Kreis made this statement perhaps a few decades back, even today our eyes and the human retina is not sophisticated enough to determine the effect of changing illumination conditions on the nature of light, on the nature of appearance of color. It is only through various mathematical operations and various instrumental procedures that we actually try to model the appearance of color or simulate the appearance of color under different lighting conditions, under different chromatic conditions. So it is very heartening to know that his lamentation, his possible lamentation that he said in this statement, that perhaps later on, if our eyes becomes very sophisticated enough to understand the effect of light on a color, then people in the future will recall this with pitying smiles. But still today, no such, our eyes have not evolved in such a way so that it will be able to understand or fully realize the impact of that ambient light or illumination condition has on visualization or appearance of colors. So various color appearance modeling has been made over the course of time. CI, CAN 2002 and all of this has been made. That is not the scope of this class, but I just wanted to give you a very brief bird's eye view of the process in order to calculate or fully understand how colors are visualized across platforms, across devices and all of this. So simply finding out Euclidean distances and incorporating some other parameters, this is not enough. We need to consider various other parameters, as I mentioned previously, in order to fully model the appearance of color or the changes in appearance of color under different lighting conditions. Okay, so I think with this we come to an end to colorimetry part of in color science. In the next part, in the next session, we will be talking about color management. That will be the next component. We will start color management from the next slide, next lecture. Okay, thank you.